Between 2007 and 2013, Chinese military hackers extracted over 50 terabytes of classified data from American defense networks. Included in that haul, blueprints, schematics, and performance parameters of the F-35 Lightning II, the most expensive weapons platform in human history. 5 years later, China unveiled a fighter jet that looked nearly identical. The resemblance was not coincidence. It was theft at industrial scale. Pentagon analysts called it a strategic disaster. Media outlets warned that American air dominance had been copied, stolen, and weaponized. The fear was immediate. If China had the blueprints, did they also have the fighter? The answer would hinge not on what was stolen, but on what could not be replicated. Because while blueprints can be copied, the invisible sciences behind them cannot. And one critical flaw would render China's imitations strategically useless. For 70 years, American air superiority has been a foundational pillar of military power. From the Korean War to the Gulf, control of the skies enabled everything else: precision strikes, troop movement, intelligence gathering, deterrence. That dominance was never accidental. It was engineered. The United States invested trillions in propulsion research, radar physics, avionics integration, and materials science. Entire institutions, NASA, DARPA, Pratt & Whitney, Lockheed Martin, spent generations building knowledge that did not exist elsewhere. By the early 2000s, that advantage had crystallized into the F-35 program, a fifth-generation stealth multi-role fighter designed to replace legacy aircraft across the Air Force, Navy, and Marine Corps. Its goal was not just incremental improvement. It was generational leap. Stealth geometry, sensor fusion, network-centric warfare, sustained supersonic cruise without afterburners. Cost: $1.7 trillion over its lifetime. But China was watching, and China was patient. While the US poured resources into engineering breakthroughs, Chinese intelligence services pursued a different strategy: infiltration. Rather than replicate decades of expensive research, they would simply take it. Starting in 2007, hackers believed to be linked to China's People's Liberation Army began probing American defense contractors. The attacks were quiet, persistent, and sophisticated. They targeted not frontline military systems, but the supply chain: subcontractors, software vendors, engineering firms that handled pieces of classified programs. No single breach triggered alarms. No catastrophic data dump made headlines. Instead, the theft was incremental, surgical, distributed across years and dozens of networks. By 2013, forensic investigators discovered the extent of the compromise. Files related to the F-35's airframe design, avionics architecture, and radar cross-section modeling had been exfiltrated. So had technical drawings, maintenance protocols, and performance data. The Pentagon classified the breach as one of the most damaging acts of espionage in modern military history. And then, in 2014, China debuted the J-31. The resemblance was unmistakable. Twin engines, swept wings, chined fuselage, internal weapons bays, sensor arrays mounted identically. Defense analysts compared images side by side. The J-31 was not inspired by the F-35. It was a copy. The question now facing American strategists was existential. Had China leapfrogged a decade of research at a fraction of the cost? Could a stolen design neutralize America's most expensive technological advantage? The world assumed yes. The engineers knew better. From Beijing's perspective, the logic was flawless. China needed a fifth-generation fighter to counter American and allied air forces in the Pacific. Developing one from scratch would take decades and cost hundreds of billions. Even then, success was not guaranteed. Indigenous Chinese fighters had never matched Western performance. But if the blueprints already existed, if the hardest problems had already been solved, then the path forward was clear. Steal the design, reverse engineer the systems, deploy the aircraft. And that is exactly what appeared to happen. In 2014, the J-31 made its first public appearance at the Zhuhai Air Show. Chinese state media promoted it as a next-generation stealth fighter, designed for export and carrier operations. Promotional materials emphasized its low radar cross-section, internal weapons carriage, and advanced avionics. Foreign military observers immediately noted the visual similarities to the F-35. The airframe geometry was nearly identical. The cockpit layout mirrored American design philosophy. Even the landing gear configuration matched. Western analysts began referring to it as the F-35 clone. Media coverage amplified the narrative. Headlines warned that China had stolen America's edge and copied the future of air combat. Politicians demanded investigations. Defense forums debated whether the U.S. had lost its technological moat. China did nothing to discourage the perception. In fact, Beijing used it strategically. If adversaries believed China possessed a stealth fighter equivalent to the F-35, deterrence worked without firing a shot. Regional rivals would reconsider aggression. Arms sales would increase. Strategic negotiations would tilt. For a few years, the illusion held. The J-31 appeared at airshows. Promotional videos circulated online. Defense journals speculated about variants for the People's Liberation Army Navy, adapted for aircraft carriers under construction. China projected confidence. But behind closed doors, engineers faced a problem they could not solve with stolen files. The airframe was complete. The shape was correct. The blueprints had been followed precisely. But the aircraft could not fly the way it needed to, because the most critical system, the one that determined whether the J-31 was a world-class fighter or an expensive shell, had not been stolen. It had been built, molecule by molecule, over decades, and China did not know how. The F-35's true advantage does not lie in its shape. It lies in what powers it. At the heart of the Lightning II is the Pratt & Whitney F-135 engine, the most powerful fighter engine ever built. It generates 43,000 pounds of thrust. It enables sustained supersonic cruise without afterburners, a capability called supercruise. It integrates seamlessly with stealth geometry, minimizing heat signature and radar return. But the real engineering marvel exists at the atomic level. Inside the F-135's turbine section, temperatures exceed 3,000 degrees Fahrenheit, hotter than lava. At those extremes, metal does not simply weaken. It begins to melt, oxidize, and disintegrate. To survive, the turbine blades are manufactured from single-crystal superalloys. Unlike conventional metals, which are composed of millions of microscopic grains that can fracture under stress, single-crystal alloys are grown as one continuous lattice structure. No grain boundaries. No weak points. The process is extraordinarily difficult. It requires directional solidification in vacuum furnaces, where molten metal is cooled at precisely controlled rates. A single miscalculation, temperature variance of a few degrees, contamination from impurities, vibration during cooling, ruins the blade. Pratt & Whitney, General Electric, and Rolls-Royce spent 40 years perfecting this process. It requires not just machinery, but institutional knowledge, metallurgists who understand alloy chemistry, engineers who calibrate furnace parameters, inspectors trained to detect microscopic flaws. That knowledge cannot be stolen. It cannot be reverse-engineered from blueprints. It must be built, tested, failed, refined, and mastered over generations. China's hackers extracted terabytes of data. They obtained airframe schematics, avionics diagrams, and radar models. But they did not obtain the decades of foundry experience required to forge single-crystal turbine blades at scale. And without those blades, the engine fails. Without the engine, the fighter cannot perform. Stealth geometry becomes irrelevant if the aircraft produces a visible smoke trail. Sensor fusion means nothing if the jet cannot reach the battlefield. Network-centric warfare collapses if planes spend more time in maintenance than in the air. China stole the body. But the body was never the weapon. The engine was. And that could not be copied. The consequences became visible the moment the J-31 began sustained testing. Chinese engineers installed the best engines they had access to, variants of the Russian-designed RD-93, a decades-old turbofan derived from the MiG-29's power plant. It was reliable, widely available, and combat-proven. It was also inadequate. The RD-93 uses polycrystalline turbine blades, standard metallurgy with grain boundaries that limit heat tolerance. To compensate, the engine runs cooler and less efficiently. Thrust output, 19,000 pounds per engine. The F-135 produces 43,000 pounds. From a single engine. The math is simple. Two RD-93 engines generate 38,000 pounds of thrust combined, still less than one F-135. The J-31, despite having twin engines, is underpowered relative to its airframe. It cannot supercruise. It cannot sustain high-G maneuvers without bleeding energy. Its operational range is reduced. But the performance gap is only part of the problem, because the RD-93 was never designed for stealth. At full throttle, it produces a visible smoke trail, a consequence of incomplete combustion and older fuel atomization technology. That smoke is detectable by infrared sensors from hundreds of miles away. Stealth is destroyed instantly. The entire purpose of the J-31's carefully sculpted airframe, the faceted surfaces, the internal weapons bays, the radar-absorbent coatings, is negated by an engine that announces its position to every sensor in the battlespace. China attempted solutions. Engineers tested domestic alternatives, including the WS-13 and WS-19 turbofans, developed specifically to replace Russian engines. Early prototypes showed promise. But mass production revealed the same metallurgical limits. Without single-crystal turbine blades, the engines could not sustain high temperatures without degradation. Service life was measured in hundreds of hours instead of thousands. Maintenance cycles increased. Operational readiness plummeted. By contrast, the F-135 is rated for 8,000 hours between overhauls. It integrates health monitoring systems that predict failures before they occur. Maintenance crews can swap modules in hours, not days. The F-35 spends 60 to 70% of its time mission ready. The J-31 spends more time in hangars than in the sky. China's attempts to reverse engineer advanced turbine manufacturing hit the same walls repeatedly. Foundries lacked the precision equipment. Metallurgists lacked the baseline knowledge. Quality control failed to detect microstructural defects that only appeared under sustained combat stress. By 2020, reports emerged that China was purchasing additional RD-93 engines from Russia, not as a stopgap, but as the only viable solution. The implication was clear. China could replicate the appearance of a fifth-generation fighter. It could not replicate the propulsion system that made it effective. And without that, the J-31 was not a strategic threat. It was a demonstration model. Pentagon analysts adjusted their assessments accordingly. While the J-31 would still be marketed to export customers, nations without access to American stealth platforms, it would not challenge U.S. air dominance in contested environments. Because dominance is not determined by aesthetics. It is determined by engineering depth. The F-35 was designed around an engine that took 40 years to perfect. Every system, from thermal management to electrical generation to flight control authority, was built assuming that engine's capabilities. China copied the systems, but the systems were designed for an engine China did not have. The result was an aircraft that looked like a Predator, but performed like a prototype. And in air combat, performance is survival. The engineers who spent decades perfecting single-crystal turbine metallurgy did not do so for marginal gains. They did it because they understood a fundamental truth. In high-technology warfare, there are no shortcuts. Physics does not negotiate, and genius built over generations cannot be stolen in a data breach. China did not abandon the J-31. Instead, it recalibrated expectations. By 2021, the People's Liberation Army had not adopted the J-31 for frontline service. The aircraft remained in development, with focus shifting toward export markets and potential naval variants. Chinese defense officials emphasized its role as a technology demonstrator rather than an immediate operational platform. This was not an admission of failure. It was strategic adaptation. China redirected resources toward indigenous engine development, pouring billions into turbofan research, advanced materials institutes, and metallurgy programs. The goal remained clear: eliminate dependence on foreign propulsion systems and close the performance gap with American engines. Progress has been incremental. The WS-10 and WS-15 engines, designed for China's J-20 stealth fighter, represent improvements over previous generations. They incorporate better thermal coatings, improved fuel efficiency, and higher thrust output. But they still do not match the F-35. Single crystal turbine blade production remains inconsistent. Yield rates are low. Service life lags behind Western equivalents by thousands of hours. China's approach now mirrors the Soviet Union's during the Cold War, accept temporary inferiority while building the institutional knowledge required to compete long-term. That process will take decades. Meanwhile, the United States has not remained static. Lessons from the 2007 to 2013 espionage campaign triggered comprehensive cybersecurity overhauls across defense contractors. The Pentagon implemented stricter network segmentation, insider threat monitoring, and supply chain vetting. New protocols assume persistent adversary presence and design systems accordingly. More importantly, American engine development continued. Pratt & Whitney's next-generation adaptive cycle engines, designed for sixth-generation fighters, incorporate variable bypass ratios, allowing pilots to optimize thrust and fuel efficiency in real time. These engines are expected to deliver 10% more thrust and 25% greater range than current models. The performance gap is widening, not closing. China's espionage operations succeeded tactically. Terabytes of data were stolen. Blueprints were copied. Airframes were built. But strategically it failed. Because the goal was not to steal information. The goal was to neutralize American air superiority. And that requires more than stolen files. It requires the decades of unsexy, unglamorous work that happens in foundries, laboratories, and test cells, work that cannot be accelerated by espionage. China learned this the hard way. They obtained the design. They could not obtain the capability. And in military technology, that distinction is everything. The J-31 exists today as a reminder that imitation has limits. Stealth airframes can be copied. Radar cross-sections can be measured. Avionics architectures can be reverse-engineered. But the invisible sciences, metallurgy, thermodynamics, manufacturing precision, resist theft. They are not contained in blueprints. They are embedded in institutions, in experienced engineers, in trial and error processes repeated thousands of times until mastery is achieved. This is why American air dominance has persisted for 70 years. Not because adversaries lack ambition or resources, but because true technological superiority cannot be shortcut. China's experience with the J-31 reinforces a principle that has defined military competition since the Industrial Revolution. In high-technology warfare, depth matters more than speed. A nation can steal a decade of research. It cannot steal a generation of expertise. The F-35 remains the most advanced multi-role fighter in service. Over 1,000 have been delivered to the US and allied nations. It operates from carriers, austere airfields, and forward bases across the Pacific, Europe, and Middle East. China's J-31 flies at air shows. The difference is not luck. It is engineering. And as long as the United States continues investing in the foundries, laboratories, and test programs that produce breakthroughs like single crystal turbine blades, that difference will persist. Because shortcuts are tempting. But physics does not compromise. And dominance is not stolen. It is built. If you want to understand how engineering decides wars before the first shot is fired, subscribe. More stories like this are coming. The details matter, and the details are everything.